this video, we are going to learn some examples of function spaces. Before we go for the examples, let us first recall what we have done in the earlier video. We have seen various norms on Rn, and then we have seen the norms even on sequence spaces. So, just to summarize quickly, let us see that an element in Rn looks like having n coordinates, whereas in sequence space it looks like having infinite coordinates. Then we have defined norm 1 on Rn as mod xk summation running from 1 to n, whereas on a specific set it is the infinite series mod xn n running from 1 to infinity. So, we had to restrict our set, if you remember at that time. Then norm 2 we have defined on similar lines, and even norm infinity we have seen it is the maximum of mod xk, where k run from 1 to n for Rn, whereas we have to change it to supremum because now we have infinitely many terms in the set. We may have infinitely many terms in the set, and then we have to take its supremum instead of maximum. Now, the question is, how do I extend it further? That is, now instead of countably many, we may have something like uncountably many components. In other words, we would like to talk about functions from closed interval to R. So, that is what we would like to get into. So, let us take the set as CAB, that is the notation for set of all continuous functions which are real valued functions on closed AB. Now, this is what we are taking as our set. There is a reason why we are not going to take all possible functions. Let us see why. Before we go for that, let us define norm 1 on similar lines, what we did in Rn or R omega for that matter. So, let us take any function f in CAB. Norm f, I would like to define it as something like the sum of all the function values. So, here it gets replaced by the integration over AB of mod ft dt. So, this is the intuitive norm that we can have, norm 1 on CAB. Now, using it, first of all, is it a well defined norm? You must have seen that if f is a continuous function, then mod f is also continuous, and further every continuous function is Riemann integrable, and hence this is certainly a well defined norm. There is no problem in well definedness. In fact, using the properties of Riemann integration, we can also prove that it is a norm. And going ahead, now let us look at the corresponding metric, that is D1 metric we would like to denote it by. Then it is going to be norm of f minus g, which is nothing but the integral a to b mod ft minus gt dt. Now, we would like to even know how geometrically, what geometrically this means. So, for that let us take say two functions f and g, and let me take a interval a to b here. Okay. Now, let us have the curves of f and g as this. This is the curve of f that I can have, and let me draw a curve of g, function g, something like this. So, this is a g function. I want to know now that what this distance between f and g represents. Then if you observe very carefully, it is mod ft minus gt is what I want to now look for. So, if I take any point over here x or rather t, then corresponding f of t is here and g of t is here. Okay. And now ft minus gt is always going to be the length of this line segment. So, going in this way, we can actually observe that this represents basically the area between ft, the curve graph of f, and the graph of g. So, this is what exactly is going to give me the d1 distance between functions f and g. So, the d1 distance between f and g is nothing but the area of the region between the curve of f and the curve of g. So, this is the idea of norm 1. Now, going ahead, before we go ahead, let us ask a question. The question is, instead of CAB, if we would have taken RAB, that is set of all real valued Riemann integrable functions on closed AB, and define DFG as integral a to b mod ft minus gt dt. The question is, which property is not satisfied by this function d to become a metric? So, I am already disclosing one information, that it is not a metric, but now I want you to think about which property fails by this function to become a metric. I take a pause here, you can pause the video for some time, work out and then continue the video. So, I am sure you must have worked it out. Let me disclose the answer. The answer is definiteness is the property that in fact fails. And why does it fail? Because only Riemann integrability is not sufficient, because we may have a function which is Riemann integrable and the area below that function is 0, but the function may take some non-zero values. Hence, we cannot guarantee the definiteness property, that is distance between f and g may be equal to 0, but f and g may not be equal throughout. Thus, we cannot take RAB for defining this particular metric, we need to take CAB. Now, going ahead, let us have two more norms which we already have seen on Rn or R omega. Let us see whether we can extend those norms over CAB. So, norm 2, you can expect how am I going to define norm 2. So, take any function f in CAB, then norm 2 is going to be, you take the integral of mod ft square and then take the square root. So, this is going to be a norm on CAB and the corresponding metric looks as follows. So, d2fg is integral a to b ft minus gt whole square dt and then take the square root. This is certainly a norm on CAB. Now, let us look at the third norm that we can consider, that is norm infinity. Now, norm infinity again on similar lines we would like to define, that is you need to take a supremum of all modulus of all the values of the function. So, supremum of mod ft t belongs to closed AB. Again the question is it well defined? Then the answer is going to be yes, because if I have a function continuous then on closed and bounded interval, then it is going to be bounded and its supremum is certainly going to exist, and hence I can define norm like this, it is a well defined norm. And on same lines I can then look for d infinity, that is the distance which is norm of f minus g, which is supremum of mod ft minus gt. In fact, we also would like to see the geometry, that is geometrically what this represents. So, if I want to see the geometry, let me draw the axis, let us consider the points a and b. Let me get my first function f to be, this is the curve of function f, and there is another curve which is of function g. So, let me draw another curve which is representing function g. Now, I want to see what this d infinity distance represents. So, what you simply have to do is at each t between a and b, look at the corresponding point on f, that is f of t, and corresponding point here, look at the length of this line segment, and this is what I have to do at every t. I have to see the corresponding length of the line segment and then all these lengths I have to consider, and then I want to take the supremum of all these lengths, that is going to represent the d infinity metric on CAB in fact. So, this is the geometry of d infinity metric. Now, just to summarize, let us see what we have. So, let us have all the examples in one stroke, that is we have Rn, we have sequence spaces and we have CAB. If you observe carefully, Rn we denote the term as x1 x2 xn any element, then we can extend it to x1, x2, xn and so on, that is the member of a sequence space, and the similar kind of a element in CAB looks like a function from closed AB to R, and we restrict it to continuous functions just to get the well definedness of the objects, or more properties. In fact, we need norm and hence we have to take continuous functions. Then if you look at norm 1, you can see the similarity between the norm 1 over Rn over sequence space and over CAB. Norm 2 you can see the similarity, and even norm infinity you can see that all these norms are defined in similar pattern. So, this is the summary of the examples that we have seen till now. I request the students to go through more exercises that are provided along with these videos.